Okay, for y equals x squared, we're going to put in x squared every place that we see a y. So we're looking at f of x squared instead of y is equal to x times x squared in our numerator, and then the square root of x squared plus an x squared getting squared in the denominator. We have to simplify this. This gives us x cubed. And then in the denominator, there's an x squared in common that we can factor out and take the square root of. On the outside, it'll be an x, and inside we'll be left with a 1 plus an x squared. This simplifies one more step. We get x squared over the square root of 1 plus x squared. And now we can take the limit on this, and again, we're using our nice notation. F of x comma x squared is x squared over the square root of 1 plus x squared. And if I go ahead and let x go to 0, this whole thing is going to go to 0 as x goes to 0. Okay, that's 4 paths. We need to try one more. I'm going to go with x equals y squared. Okay, so that one is over here, sideways parabola. This picture is super messy now, but hopefully you've seen it as it's been growing. So we're looking at x equals y squared, and this means that everywhere there is an x, we're going to replace it with y squared. So we're looking at f of y squared y. And we go to our function, everywhere there's an x, so in the numerator there's an x, I'm going to put in a y squared. In the denominator we have the square root of, and now I'm going to put in a y squared, all squared plus y squared. This simplifies to be y cubed over, and I can factor out a y squared in the denominator and then square root it. Outside it'll be just y. Inside we'll be left with y squared plus 1. One more simplification leaves us with y squared over the square root of y squared plus 1. Now, in this particular one, if I look at f of y squared with y as y squared over the square root of y squared plus 1, and I go ahead and I let y go to 0, I'm going to get a 0 in the numerator, and that 0 over anything is 0, so this goes to 0 as y goes to 0. Okay, that's 5 paths, and in 5 paths I've gotten 0 every single time. So I kind of want to prove that I actually have a limiting value of 0. So just to say that, 5 paths all go to 0 in the limit. So we have to use the squeeze theorem to prove this, or to prove the limit is 0. Okay, so we have to start out with something that's true, and typically we start with an inequality when we're using the squeeze theorem. So I want to start with our numerator, and not the full numerator, just part of it. So I'm going to start with absolute value of x, and I'm looking at absolute value of x so that I'm just looking at one side of 0. A very similar, equivalent inequality could be shown for negative values of x. Now the absolute value of x, I can say with all certainty, is greater than or equal to 0. I can also say that it is equal to the square root of x squared. If I take the square root of x squared, I'm going to get the value, the absolute value of x. So that's something that's true, but that's not quite an inequality, okay? So I need to make this an inequality, and the way I can do that is I'm looking at my denominator. Maybe I should rewrite what my original function was. The original function was xy over the square root of x squared plus y squared. Just so I kind of have this in my vision here. So my denominator doesn't just have a square root of x squared. It has a square root of x squared plus y squared. So I'm going to rewrite my inequality. The absolute value of x is greater than or equal to 0. And then I'm hoping I can get a less than or equal. And I still have my square root of x squared. And now I'm going to add something more into my square root, which is going to make the overall number bigger for all values of x and y. So I'm going to add in a y squared. Okay, now that I have that, what I want to do is divide all sides by the square root of x squared plus y squared. Because the square root is positive, we know that dividing by it will not introduce a need to flip the inequality symbol. So we're okay there. So if I divide on the very left, 0 over anything is 0. I get the absolute value of x over the square root of x squared plus y squared in the middle. And on the far right, if I divide something by itself, I get a 1. Okay, we're getting somewhere now. Now, the guy in the middle, that's supposed to represent our function, except it's not quite there. It's missing the y from the numerator. So I'm going to go ahead and put it in there. So we're going to multiply all sides by the absolute value of y. And again, I'm using the absolute value to ensure that I'm dealing with a positive number so that I don't get this flipping of the inequality symbols going on. So when I do that, I multiply the 0 by the absolute value of y, and I get 0. In the middle, I get the absolute value of x, y. I can bring them both in the absolute values. I still have my same denominator, square root of x squared plus y squared. And on the right, 1 times the absolute value of y is just the absolute value of y. Okay, this guy in the middle is our function. Now it's the positive aspect of our function. It's the side where if x and y were both positive or both negative, then we could get that. As I said before, we could do a similar proof for the negative values or where x and y are opposite in sign. We're going to focus on just looking at this positive side, and similarly, the approach from the other side would be the same. So now we're going to take the limit of all sides. And what I get is the limit as xy approaches 0, 0 of 0 is less than or equal to the limit as xy approaches 0, 0 of the absolute value of xy over the square root of x squared plus y squared is less than or equal to the limit as xy approaches 0, 0 of the absolute value of y. Now on the far left, we get 0. In the middle, that's the guy we couldn't evaluate to begin with. So it's just going to stay as the limit as xy approaches 0, 0 of the absolute value of xy over the square root of x squared plus y squared. And the limit as xy approaches 0, 0 of the absolute value of y is 0 as well. And so what we have here is a limit that we don't know is sandwiched between 0 and 0. Or it's squeezed. Okay, so by the squeeze theorem, our limit is 0. And that's it. We're done with that problem. Okay, so that's how you use the squeeze theorem. Notice, remember, I took 5 paths and I got the same thing every time. Now you may find in the homework that it could take 6 paths. You have to start looking for patterns and whether things are actually going to simplify to be a different number than, like, for example, in our case, 0. 0 kept coming up, but what if there had been a path I could choose that I could see that it was going to simplify to something different from 0? I wasn't seeing that with this one. So after 5 paths, I was happy to try the squeeze theorem. Okay, next topic is actually about continuity. So we have to remember our definition of continuity from Calc 1. And so a function is continuous at a point if the following 3 criteria hold. 1, the limit actually exists at the point. So you can't have continuity if there's no limit. 2, the function value has to exist at the point. That just means there can't be any holes, okay? And 3, the limit is the same as the function value. So in other words, we could do direct substitution or the squeeze theorem or some sort of trick that we've learned that will allow us to determine, like, hey, the limit value and the function value are the same, therefore we have continuity at that particular point. So we're going to look at a particular function, g of xy, and g of xy is a piecewise function with two pieces, and it's equal to xy over the square root of x squared plus y squared if the coordinate pair xy is not equal to 0, 0. Since if it was equal to 0, 0 in the denominator, things would be undefined. And then the second piece, g of xy, is going to be made equal to 0 if our ordered pair is equal to 0, 0. So I'm going to examine the first piece. That's the xy over the square root of x squared plus y squared. And it is continuous on its domain. And that domain is the set of all xy pairs such that your xy pairs cannot be 0, 0. Or I should say, actually, the way, we would typically say this is such that the denominator, x squared plus y squared, does not equal 0. Okay, so that's our domain, and it is not continuous when xy is equal to 0, 0. So that's what the domain is saying. Now, to see if g of xy is continuous at 0, 0, show that the limit as xy approaches 0, 0 of g of xy equals g of 0, 0, and that is equal to 0. If we can show that's true, then we're in business. Okay, so we've already worked with this function. We just finished a problem where we were finding the limit of the first piece. So we need to look at the limit as xy approaches 0, 0 of xy over the square root of x squared plus y squared. We found that it was equal to 0 in the previous problem, but I want to try something else. Okay, so we used the squeeze theorem before. I want to try this whole polar coordinates. So this limit can be evaluated by using paths and the squeeze theorem as in the previous problem, or by using polar coordinates x equals r cosine theta and y equals r sine theta, and letting r, no, I accidentally wrote a vector. We use r vectors so much, and letting r approach 0 from the right. Now it's going to be from the right because r is a radius, and we don't have anything that exists for negative values of a radius. Okay, so I'm going to replace all x's with r cosine, all y's with r sine, and I'm going to replace the x comma y going to 0, 0 with r going to 0 from the right. So now what we're looking at is the limit as r, I keep wanting to write a vector hat, The limit as r goes to 0 from the right. In the numerator, I have x times y, so I'm going to get r cosine times r sine. I can just write that as r squared cosine of theta, sine of theta. And in the denominator, well, we have an identity that x squared plus y squared is equal to r squared. So in the denominator, I have the square root of r squared. So the r squared in the numerator is going to simplify with the square root of r squared in the denominator to leave me 1r in the numerator. So this is the limit as r goes to 0 from the right of r cosine of theta, sine